Marlasca, who is the last speaker of the local PhD team. And then we are going to have another one from another university. So Fernando is working here, and he is going to talk about asymmetric pulsing for reliable operation on titanium manganite memristors.
Hi, good morning. I'm Fernando Marlasca, and I work under the direction of Pablo Levy. I would like to discuss some results we published last year about a way to optimize ReRAM parameters using closed-loop circuitry. ¿Dónde hay que apuntar? All the results were obtained from a very simple metal manganite sample. The metal was titanium, and the manganite was a lanthanum praseodymium calcium manganite, polycrystalline manganite. I won't be focusing so much in the sample itself. I'll be focusing more on the protocol for measuring and changing the resistance applied to it. The samples had titanium contacts, 1 millimeter wide, separated from one another 1 millimeter. Current was injected through 2 contacts, both for inducing resistance switching and for reading the non-volatile resistance after pulsing. The amplitude of the reading pulses was about 50 microamps, and they lasted 200 milliseconds. We had plenty of time to do the measurement, so we really don't care about that time. The pulsing time was slow, though. It was 1 millisecond, and the polarity and amplitude of the pulses were arbitrary. First, the amplitude of these pulses were hand-selected, and afterwards I'll show you some results about an automatic protocol. Let's focus a little on the first result. This is a result obtained from a pristine sample. The upper curve shows an arbitrary pulsing sequence of alternating polarity and increasing amplitude. Notice that in order to this sequence was increased until a change in remnant resistance was measured. And notice that to change back the resistance, a pulse with the opposite polarity and different amplitude is needed. Different amplitude. The amplitude was selected by the experimenter based on their own experience. This manual selection problem, this manual selection of the set current and reset current could lead to a drift in the high resistance state or the low resistance state. In this case, a decrease in the high resistance state is observed. Let us recall that the mechanism behind this kind of behavior was explained by Mr. Sawa, Rosenberg, and Yumaho, and some others, and it's. And I'm sorry, I want to say this properly, so I'll read it. The local electric field is the local electric field is proportional both to the local resistivity and the circulating current. If the local resistivity has changed since the last current pulse, then the electric field profile near the interface cannot be replicated. Alternating pulses with the same polarity do not produce a cancelling effect. Thus, a drift in non-volatile resistance is observed. Therefore, minimizing drift requires a better way of selecting the set current and the reset current. Our proposal was a closed-loop circuit that could prove useful in finding the set current and the reset current for counterbalancing the resistance switching drift. First, we define a lower and upper thresholds. We understand that the sample is in a high resistance state if the resistance is above the upper threshold, and we understand that the resistance is in low resistance state if the sample is below the lower thresholds. These are the thresholds. This is the same figure we just seen. It's just for moving forward in known territory. I'm sorry. Number 6. The algorithm tries to induce as many transitions low to high and high to low transitions as possible. The low to high transition and high to low transition are analogous. Just changed the pulsing polarity. So I'll describe one of them, and I'll do it very briefly. I have with me copies of the detailed algorithm, and you can also check it outside in the poster. The algorithm tries an initial set value, usually small. If this transition is successful, then this value of set current is kept, and the system tries to induce the other transition, that is to say the high to low transition. If not, another pulse with the same amplitude is injected. If the system failed the transition after the second pulse, a third pulse of larger amplitude now is injected. The system keeps injecting pulses of increasing amplitude until the transition is successful or the maximum number of pulses is allowed is reached. Again, if the transition was successful, the current value is stored. Otherwise, the sample is rejected as it doesn't not work anymore. And that recorded current value will be used in the next transition, in the next low to high transition. Let's consider the first steps of the pulsing protocol. They are plotted against cycle number, and by cycle we mean successful transition. The first panel shows the resistance recorded after the successful transition, and that's why a gap is observed in resistance. The second panel shows the evolution of the set current and the reset current. And the third and fourth panel shows the number of pulses needed to achieve a successful transition. And plus is the number of pulses needed to surpass the upper boundary, so set pulses, and minus is the number of negative pulses needed to achieve a high to low transition. Something I'm forgetting. Notice that the number of pulses needed to surpass the thresholds decreases rapidly, and eventually it finishes in one step, which is what we wanted. We wanted to switch the sample with only one pulse, and the same for the other polarity. And notice that eventually those are the first steps, but eventually the currents stabilize. I'll show you a longer measurement now. See, and the resistance in this case fluctuates a little, well beyond the thresholds, so the gap remains, and I'm sorry. And The number of pulses, okay, in the first cycles there are more than one, but in most cases, in the vast majority, with only one pulse, the transition was achieved. So the system seems to be learning well. Anyway, this is a technicism, but if we have time, every now and then it uses a second step. I'm going to read this too. Recall that the second pulse is injected with the same amplitude of the first pulse of the cycle, and the reason for it is that the algorithm tries to keep the amplitude of the set and reset currents as low as possible. So, if once in a while the sample needs a second kick, okay, we allow it. But there is a limit for the number of consecutive second chances too. The idea is to use as few pulses as possible. Well, to check the robustness of the system, we deliberately turned off the protocol. The upper image is one with the protocol on, just as a reference. And in this image, in the white shaded area, we turned off the protocol and changed the values that the protocol had reached. In this case, 110 minus 20, we changed the minus 20 to minus 90. So we changed the reset current, and we see a drift that damages the performance of the memory. And in this case, we changed the set the set current. We decreased it. We decreased the reset, but it's like increasing the set. Hello. And it drifts away from the gap, so the memory starts failing too. Well, to sum up, the algorithm succeeded in finding current bodies that allow stable operations for up to 5 to the 5 cycles. In fact, we know that 10 to the 5 it reaches okay, but we turned off the measurement when we grow tired, because every cycle demanded 1 second, so 10 to the 5 were a lot of time, and know how much will this endure. And I think that closed loop circuits could be used to extend the endurance of urban memories, as we heard yesterday with Jorge Tell. Not particularly in this protocol. I'm going to criticize a little, but closed loop circuits could result very, very useful. Well, that will be all. Thank you.
Thank you, Fernando, for this nice explanation. Do you have time for a couple of questions, Charlie?
I want to ask if you know if the flash memories use this type of protocols, or are these protocols known?
I really don't know what they use, but they use some sort of protocol, because when you are recording something in a flash, when it isn't successful, the recording, that certain bank hits cancelled. So it does use some sort of closed loop control. I was saying, if you mind, I was saying that this protocol wouldn't be very suitable, because there's one thing that makes it very bad. It uses memory to operate memory. So this is good for finding 2 values of current that could work, and then let the number of pulses go wild. But the protocol as is, it's not good.
Any other question or comment? Another one?
I wonder if there's any overheating problem with this 300 milliamperes or not.
Well, the samples were very, very big, and the contacts were 1 millimeter wide. So no, we didn't find any problems, but the samples are not real, are for this measurement purpose only.
Okay.
Do you think we can use this type of closed loop for unipolar mechanism?
Probably not this one, probably something in the continuous field, because you have to check with every voltage if you change the state or not. But I'm sure that it has to be, I mean, there has to be an application for a closed loop circuit.
Thanks.